Thanks a lot. And now we're going to listen to Enrico Cinti, who's going to talk about symmetries, causality, and emergent spacetime. Thanks a lot, Enrico.
Thank you, Baptiste. Thank you to Baptiste, Chris, and Annika for the lovely event. It's the fourth year running at least that I'm at one of these, so I feel very privileged when I'm speaking. And yes, as Baptiste said, I'm going to talk about basically, well, symmetries, causalities, and emergent spacetime. And in some sense, the starting point here is just that it's this question of understanding emergence of spacetime, which is reasonably recognized as one of the great challenges raised by the development of theories of quantum gravity, which seem to lack a fundamental spacetime description. And much has been said, much ink has been spilled on this topic, and to a large extent, a lot of the philosophical debate has been on the viability of approaches such as spacetime functionalism, and more general, on the metaphysical interpretation of emergent spacetime. At the same time, it seems to me that there are still a lot of questions that remain open when we talk about emergent spacetime, and in particular one that is sort of not often considered, but that we're going to talk about today, is precisely which physical mechanisms underlies the emergence of spacetime. And so in this sense, to some extent, where significant attention has been paid to how to conceptualize spacetime as emergent, not nearly as much attention has been paid to what drives the emergence of spacetime. And nevertheless, I think that this question is important for a variety of reasons. So first of all, knowledge of the specific mechanisms underlying spacetime emergence should ideally give us a better window into the conceptual foundations of quantum gravity and specific quantum gravity theories, which presumably are going to differ regarding what they think drives the emergence of spacetime. Different mechanisms leading to spacetime emergence might also lead to different judgments regarding the correct metaphysical account of emergent spacetime. And understanding the mechanism behind spacetime emergence should also ideally give us a window also into the fundamental ontology of quantum gravity. And to some extent, the last point is maybe especially interesting. The idea here is that emergent spacetime as an entity to some extent is described mathematically by GR viewed as an effective field theory. And in this sense, emergent spacetime is going to be quite insensitive, presumably, to the details of the underlying microscopic ontology in basically the same way in which when we do physics, an effective field theory is going to be insensitive to whatever underlying microscopic degrees of freedom we have. And so insofar as we want insights into the microscopic ontology of a specific quantum gravity theory, we need to go beyond emergent spacetime. And in this sense, just looking at the next best thing, which is just whatever drives the emergence of spacetime, so whatever mechanism is behind this, seems to be like a natural candidate for this project. So my goal in this talk will be to begin to explore this question using a somewhat simple example that I take from ADS-CFT, so holography and string theory. The example is chosen for a variety of reasons, partly, at least from my point of view, because ADS-CFT provides quite natural testing ground for ideas regarding quantum gravity, mostly because it gives a non-perturbative description of gravity, though in the context of ADS, which is admittedly unrealistic, so your mileage may vary regarding the importance of this, but it's still quite a significant step forward compared to most other approaches. And control over non-perturbative effects is quite important here, because it's quite important to understand whatever the microscopic structure of the system is going to be. Basically, non-perturbative in this context just means that we want to have exact results, not approximate ones. And without non-perturbative control, we just cannot access such exact results, and so are limited to some kind of approximation scheme like the one that Nick talked about before, using like this linear approximation. So we're going to lose a lot of the information, and especially we're going to lose a lot of the fine-grained microscopic approximation if we don't have non-perturbative control. Another important reason behind the specific example that I choose is these recent developments in the use of algebraic techniques and techniques coming from algebraic quantum field theory to study holographic field theories. These techniques are quite interesting for a variety of reasons, but in particular they give us this axiomatic and model independent window into the physics of holography, and so they give us these very general results that in principle can go beyond ADS. So in particular, one can apply this to any quantum field theory which these results are general and so such they apply to any quantum field theory that we expect to have an holographic dual. So in particular, it doesn't have to apply just to theories with an ADS dual. And indeed, there's some recent work which shows how one can find a lot of this similar structure that one identifies in an holographic field theory in ADS. They extend somewhat seamlessly to the structure, for example, of semi-classical gravity and a field theory in the Sitter spacetime, so in the cosmologically relevant spacetime. So the example then is going to use these algebraic techniques to illuminate the emergence of spacetime in holography and to give us at least a sketch of a possible mechanism for the emergence of spacetime in these holographic theories. And it will lead to some interesting insights, at least again for me, which is that, first of all, it will highlight sort of the role of symmetry in the emergence of spacetime, and in particular how emergent symmetries are, at least in this context, the crucial component behind the appearance of emergent spacetime. Second of all, we will see that there is a quite natural trade-off between having a kind of geometric or spatiotemporal description of our system and taking into account sort of all the causal properties of the underlying quantum gravity theory. Basically, we have a trade-off between having a nice geometric description and a nice causal description. This trade-off is sort of regulated exactly by this type of symmetry considerations that we're going to see drive the emergence of spacetime, and sort of as an example of this, as a nice sort of simple accessible example of this, we will be looking at an evaporating black hole as an example where we can see this quite nicely. And third, we will, by the end, be able to comment both on the role of causal relations in the macroscopic ontology of this model, sort of connecting some discussion of Baptiste and some Baron. And even more interestingly, I think we will be able to see that this trade-off between causality and geometry leads to two quite different possible ontologies for the underlying quantum gravity theory to this general relativistic effective field theory. So, let's start with this introduction. Let's start with some of the technical stuff. We'll start by saying what ADS-CFT is. An ADS-CFT is a duality, so it's an equivalence of theories between quantum gravity defined in an anti-de Sitter spacetime. An anti-de Sitter spacetime is just a maximally symmetric solution to the Einstein field equations with negative cosmological constant. So if you sort of think about our universe as a de Sitter spacetime, so a spacetime with a positive cosmological constant, here we're sort of looking at the analog of this, but with the wrong choice of signs. We have a minus in front of lambda. And this is going to be in n+1 dimensions. And then we're going to see that this is equivalent to a conformal field theory, which is a specific type of quantum field theory with conformal symmetry, local conformal symmetry. So one can basically change the scale of a theory however you want, and the theory is going to remain the same in n dimensions, so in 1 dimension less, which is defined on the asymptotic boundary of the ADS spacetime. And the idea here is that, to some extent, insofar as we believe that this CFT is well defined non-perturbatively, then since we know that the CFT is equivalent to quantum gravity in ADS, then we have a non-perturbative description of quantum gravity in ADS spacetime. And sort of to avoid leaving you just with the abstract definition, this is sort of a picture of a possible process that one can have in ADS CFT. So this is an ADS spacetime, this is an ADS black hole in particular. So these are the boundaries that I told you about. So on this sort of straight line there is a CFT living, and a sample computation that one might do in ADS CFT is something like this. So here we have a 3-point function for the CFT, so it's 3-point function because there are 3 field operators that we insert. And the way that we can compute it is of course by, well of course not, but the way that we compute it in ADS CFT is that we basically trace what is known as a Witten diagram. So something that basically looks like this, where we basically, instead of propagating in the boundary CFT, we propagate in the bulk spacetime, we have an interaction here, and then we go back to the boundary, and this gives us the conformal field theory result. This of course applies insofar as we have a semi-classical description, but we can continue to compute gravitational quantity in this way by treating, and CFT quantities in this way, by treating them as equivalent to field theory calculations basically as much as we want. So this nice geometric picture will basically break down, but the structure of a three-point function in a CFT will still make sense. So we'll still be able to compute this thing non-perturbatively. And the idea here, as I was saying, is that in a CFT, this boundary CFT allows us to define the non-perturbative dynamics of the theory, and sort of with a bit of a sleight of hand that is quite common in the physics literature, not as much in the philosophy literature, but it makes the whole discussion easier. I will sort of equivalently speak of CFT or fundamental description and ADS or semi-classical effective field theory description. I don't intend there here to be a claim of relative fundamentality between the CFT and the ADS picture, which is something that has been debated quite extensively in the literature, and the consensus seems to be that no such claim of fundamentality should be made. Here the claim is simply that the semi-classical description of this system is quite naturally given, and in some sense we will see in which sense it is quite naturally given by a gravitational field theory. And the fundamental description is at the very least only known at the moment in terms of some conformal field theory. So we don't know what the underlying microscopic quantum gravity is. We just know that it's equivalent to a CFT, and so we define it that way. So CFT here just means fundamental, and EDS just means semi-classical. Yes?
Just one thing that you mentioned before, but it's coming out also here. What motivation do we have to think that this non-perturbative aspect gets mapped through the duality?
So the motivation is that you can, in some simple examples, you can construct this. So you can check that they actually are the same. The other motivation is that, for example, in examples where you have a bit of control, like in string theoretic examples of this, what you can check is that you have basically quantities like the BPS index of the theory, which doesn't mean anything. Entropy counts of states that we know are preserved under basically changes of scale. Then you can basically take the BPS count in the fundamental theory, map it to like a perturbative description where you know what you're doing, apply a DSCFT, go down again to the non-perturbative, and you see that they're always the same. So we have all these kinds of physical arguments basically that tell us that everything we can compute sort of maps to something in the gravity description.
So is it more a case by case?
Unless you have a general proof, yes. So you have a general proof of this in the case of ADS3 CFT2. So in the gravitational theory in 3 dimensions, you can actually prove that everything is the same. If you want the general case, yes, to some extent it's a conjecture. So the validity of the conjecture is assumed here. The point is that it's a conjecture that's very heavily supported in the sense that basically any sample calculation you can imagine has been done and has been verified to very high accuracy. So basically, they haven't found a way to make this not work. But of course, there could always be some annoying little thing that we haven't been able to compute that is sitting there just waiting for us to get there and show that this is not their equivalence. But this has been, there is a lot of maths now that supports this and proofs in some sort of sample systems. So as I was saying, the idea here is that these non-perturbative dynamics of gravity end up being dual to CFT quantities, and in the sense they will at most depend, well, on the conformal structure of whatever spacetime we have, because conformal field theory is conformal. This is a lot less structured than what we're used to in spacetime, so just think that a conformal theory is a theory that has no notion of length, for example. If we go forward and take the common core approach, which is quite popular, to dualities, according to which basically we only commit ourselves to whatever is invariant under this duality map. So we only think that what exists is whatever is invariant under this transformation. Then even something like the dimensionality of spacetime starts to be something that we don't really have control over, because again, it's changing across the duality map. So the idea here is simply that we have some reasonably good evidence to say that the fundamental degrees of freedom in ADS-CFT do not admit a straightforward space-time interpretation, so they're probably non-geometrical in the same way in which general relativity is geometrical, and so they are sort of this is the right type of system to ask questions about space-time emergence. Now, how do we actually recover semi-classical space-time when we do ADS-CFT in an holographic theory? Well, the idea is that spatiotemporal degrees of freedom, again, minimally understood by some sort of effective field theory in the bulk, which reproduces semi-classical gravity. We describe them the assumption that's called bulk reconstruction. Bulk reconstruction basically aims at understanding how local bulk quantities, so something like the small interaction point that I showed you in the diagram before, that we can define in semi-classical gravity, get represented in whatever non-perturbative definition of quantum gravity we get from the CFT. This is crucial to understand emergence of space-time, since, of course, it ends up connecting the emergent quantities of the bulk semi-classical gravity theory with whatever fundamental non-perturbative description we have and from which space-time should emerge. The crucial concept when we do bulk reconstruction, for bulk reconstruction, is this concept of entanglement wedge reconstruction. We won't go into too much detail into defining what an entanglement wedge is because it's a bit of an annoying definition. But the concept is that given a spatial subregion B on the boundary theory, there is going to be some bulk region, WB, which we call the entanglement wedge of B, such that this conjecture holds. The entanglement wedge reconstruction conjecture holds. This, again, assuming ADS-CFT, this can actually be proven. We said that all physical quantities in WB, so all operators, for example, in WB, all states in WB, get represented in the conformal field theory by operators, for example, in B. So we can basically reconstruct all the physical data living in WB in terms of physical data in B. Now, as a little aside, sort of, it is the case that the map between WB and B is a linear map, but it's not necessarily an isometry, so it does not necessarily preserve inner products, and it gets evaluated just in perturbation theory in Newton's constant. This is sort of something that I won't go into too much detail in, but I wanted to mention it mostly for the fact that really, in some sense, this single sentence lies behind a lot of what I'm going to say, but again, it would have been quite too complicated to get into that in detail, but that's the formal reason why a lot of this happens. Now, an important point for what I'm going to say is that given two boundary regions R and R prime, the entanglement wedge associated to the reunion will in general be larger than the union of their entanglement wedges. A natural example here is the black hole interior. While no boundary region has access by its entanglement wedge to the interior of a black hole, because you can't send a signal and the signal cannot come out, if we take the union of all boundary regions, so the whole boundary, then the entanglement wedge will include the interior, since the entire ADS spacetime can be reconstructed from the boundary. And this is sort of an example. So if we have this interior operator here, this phi x operator, R1, R2, and R3, these are their entanglement wedges. You can see that none of them actually intersects phi x, so we cannot reconstruct phi x from any of these places. But if we get, for example, the union of R1 and R3, then the entanglement wedge of the union of R1 and R3 actually includes phi x. So it actually reconstructs the interior of this spacetime. Now let me slightly shift gears now and talk a bit about algebraic quantum field theory. This is going to be sort of the second pillar of this construction, and then at the end we're going to see how they come together. So the idea here is that algebraic quantum field theory, if you're familiar with it, describes quantum field theories in terms of an assignment of operator algebras, AR, so particularly are going to be von Neumann algebras, to spacetime regions R. So this is technically called the net of operator algebras. The assignment of operator algebras must respect a variety of axioms to count as a model of algebraic quantum field theory. So this is a completely axiomatic characterization of quantum field theory. And two examples, just to get a sense of what we are talking about, of the relevant axioms are these isotony and microcausality axioms. So isotony is sort of also called the net property because it says that if I have an inclusion of regions in spacetime, then I have an inclusion of the algebra that are associated to those regions. Microcausality, on the other hand, it's a causality condition. It says that if R and R prime are space-like, then the algebra of operator associated with R and that associated with R prime commute with each other. So again, we cannot have space-like propagating influences. Both axioms, in some sense, are encoding certain causal and locality properties of a quantum field. As I said, microcausality, for example, says that space-like separator observables commute, and so cannot influence each other. They cannot do anything to each other. An important property that a net of operator algebras can have, though it is not an axiom in the sense that it can be violated in some models, is this additivity property, which is what is going to sort of concern us when we think about spacetime emergence. Additivity basically says that if we take the smallest algebra, which contains these two algebras, for example, as sub-algebras, that is going to be the same algebra as the algebra associated to the union of these two regions. So we can exchange sort of, this doesn't really have a name, but like the minimal complete algebra for AR and AR prime with the algebra associated with the union of R and R prime. Additivity in this sense is a kind of causality, is a kind of completeness property, it's a kind of causality completeness property. It says that by joining two regions, there is no additional operation that we can perform than those that we would be able to perform in those two regions. We cannot do anything more. There is no causal interaction that we can create that was not already in the two regions. Sort of in this slightly more causal language, there is no intervention we can perform on a quantum field in the union of two regions that does not correspond to intervention in one of the two regions themselves, or some complex combination of them. Additivity, however, can be violated. An important case here, where it is violated, is in the presence of global symmetries. And sort of just, again, to get a sense for what this means, let me give you sort of a quick heuristic rundown of what's happening. So heuristically, basically, you can just think that when we are dealing with global symmetries, we can have an operator representing the charge in a given region. This operator is going to be a conserved quantity because we are dealing with a global symmetry. So this operator must commute with all operators in the algebra associated to the region, which means that it must live in the center of the algebra. Now take the algebra associated to the union of two regions. There's going to be some, again, charge operator associated to the union of these two regions in this algebra, representing the charge in that region. This operator is not an operator in R nor in R prime, since it is not supported there. I cannot just basically write it as something that is in R. It also does not live in the minimal union of AR and AR prime, since by construction it must commute with all operators there, because it must commute with all operators in this region, in this algebra, sorry. So additivity must be violated because of global symmetries, since these algebra here must be contained in this algebra here, because this algebra does not include JR union R prime, but this one does. So this is sort of the heuristic explanation of why global symmetry make problem for additivity. Now, failures of additivity are especially important for our story regarding entanglement wedge reconstruction. This sort of discussed in quite a lot of detail in this paper by Utersen and Liu. Because if we take a dual CFT to be given by a model of algebraic quantum field theory, then in the semi-classical limit, so when we recover semi-classical spacetime, additivity must fail for the operator algebra generated by this conformal field theory. The intuition behind this claim is somewhat intuitive from what we said before about entanglement wedge reconstruction. So recall that we said that the entanglement wedge reconstruction, the entanglement wedge of the union of two boundary regions can be larger than the union of their entanglement wedges. Moreover, from entanglement wedge reconstruction, it also follows that the operator algebra associated to a boundary subregion is the same as that of its entanglement wedge. And this is sort of the resulting picture. If we take just the union of these, so in some sense the minimal algebra that we defined before, we can only reconstruct this region. But if we take the entanglement wedge, so the operator algebra associated to the union of these two boundary regions, which are annoyingly called R minus and R plus, unfortunately, but they are our R and R prime, we are going to get this larger region. So we're going to be able to access more operators than we would have been just by taking the minimal union. So additivity must fail in the semi-classical limit. The algebra of the union of the entanglement wedge, must be larger than the combined algebras of the entanglement wedges of the two subregions. Failures of additivity in this sense are required for entanglement wedge reconstruction, and failures of additivity are connected to the presence of global symmetries, as we just said. Can we connect these two facts and say that the semi-classical limit and spacetime in ADS-CFT is associated to the presence of emergent global symmetries? This is sort of the question which ideally should solve. If the answer is yes, then we have sort of found in which sense symmetries are behind the emergence of spacetime, because it's the emergence of these symmetries that allows us to get additivity and so to recover the geometric picture. And the answer is yes, interestingly enough, otherwise the talk would end quite abruptly. And this is shown sort of in this couple papers by Shagulian, where it shows that in the semi-classical limit of an holographic field theory, there is an emergent global symmetry which ends up being crucial to understand the variety of the features of emergent spacetime. This happens with something that's called an Eguchi-Kawai mechanism. And the idea here is basically that, for example, if we want to look at the phases of a gravitational theory or something like the Bekenstein-Hawking wall entropy, their emergence in the semi-classical limit of this holographic field theory is justified by the emergence of this new global symmetry, and in particular by its pattern of symmetry breaking. So there is an emergent symmetry which breaks in a specific way. The way that it breaks characterizes the different phases of the gravitational theory, and also, even more importantly, I guess, is what lies behind the appearance of the Bekenstein-Hawking wall entropy formula. There is even an argument here, which we're not going to go into the details of, where even the fact that the bulk dual corresponds to some weakly coupled string theory can be understood as a consequence of this emergent global symmetry. So without this emergent global symmetry, we wouldn't even have string theory in the bulk, which you might enjoy, I suppose. So the observation clauses are circular in this sense. The emergence of spacetime in holographic field theories ends up being understood as a consequence of the emergence of a global symmetry from the fundamental description upon taking a semi-classical limit. An important aspect of this construction is that the global symmetry, and so as a consequence the failure of additivity, are in general only emergent. They're usually not fundamental. This symmetry is usually not there fundamentally, as the fundamental description can still satisfy additivity. It is the semi-classical one that does not, if we have an holographic theory. So in an holographic theory, just to restate, the failure of additivity is going to be emergent, and the fundamental theory, the fundamental CFT, will, at least in general, be additive. And so will be causally complete in the sense that we described. So sort of, how do we make sense of this? Yes?
Could you just go back to the additivity? I'm sorry, to get back to... Why do we want additivity?
Because it tells you, well, I knew someone would ask this.
You can answer later if you prefer.
No, it doesn't really...
But you don't expect it to be true in general in algebraic quantum field theory.
You expect it to be true in a theory of gravity. It's something that's called the completeness conjecture. It's somewhat annoying to explain. So the point is that this... Now, okay, let me take a minute and I'll try to explain it. The point is this. These charge operators that I was defining before when I gave you the operator, when I gave you the quick heuristic argument for why additivity is not true in general, there are going to be some kind of Wilson loop that measures sort of the charge in a certain region. Now, if you have any gauge field theory, so if you have any old quantum field theory, then those Wilson loops are going to be you're going to be able to perfectly measure them just by sort of sitting outside the loop and measuring something like the curvature of the electromagnetic field. You're going to be able to measure sort of the charge of that region just by doing that. The problem with doing this in a theory of gravity is that in general, the region picked out by the Wilson loop will never be diff invariant. So there will be very few Wilson loops that you will be able to measure in this way. So the way that you actually end up measuring, measure the charge in a certain region in a gravitational theory is that you need to have some charged particle. You send two charged particles into this region and you measure the interference effect between them as they cross the Wilson loop, and then you pick them out outside and you see sort of how they differ. The point is that to do that, you need to have the charged particles in questions. And to have the charged particles in question, you need to have an additive theory. So the condition to be able to measure any Wilson loop in a gravitational theory requires this completeness condition that requires the algebra to be additive. Otherwise, what you end up with is that you are going to have some operators that you can define that describe some physical property of your fields, even in the semi-classical regime, that you cannot measure. There is some physics that, for some strange artifact of how diffeomorphism invariance behaves, you will never be able to access. And usually this is characterized as a failure of completeness. So you want these complete algebras, basically. That's the reason. There are further arguments in favor of this. Another reason why you might want to think, actually this comes up later, that your algebra should be additive is that you have theorems in AdS-CFT which basically show you that there cannot be global symmetries in AdS-CFT. So that would be another reason. So you cannot have a global symmetry, so you need to have an additive theory.
Okay. But I'm right that this is not a normal property of
No.
fields because
Yeah.
we have non-local effects.
Yeah. No. In a normal, like, vacuum Maxwell does not have an additive algebra. Like, it's the world is full of 99% of, if anything, this completeness condition is often treated as one of these, if you're familiar with them, one of these swampland conditions, which are supposed to characterize the quantum field theories which admit completion as a theory of quantum gravity. So this is actually supposed to be something like a measure zero set of all quantum field theories. So it's a somewhat rare property, but it's needed in order to have you need to have a complete charge spectrum in a theory of gravity in order to be able basically to measure all the charges you can actually have. Otherwise you just can't, because you can't sit outside of the region unless it's a boundary.
Sorry, can I ask?
Yeah.
I guess a question, but what is the difference between additivity and separability?
What do you mean by separability here?
That's the properties of joint regions Bernese on the properties of the
Because additivity is only at the level of the algebras, it doesn't tell you that you cannot have a non-separable state. So you could have an entangled state on top of that.
Okay.
So you could have correlations between the two regions, that's not forbidden. But the point is that there is no further operator that you can add. There is no further operator in the algebra of the union that is not in the two algebras or in some combination of them. Okay?
Okay.
Separability is a property of the states of your theory. It tells you that you can only have states which basically you can write down as product states. These happens only at the level of operators. So, and it's fine to take arbitrary linear combinations of operators in here. You're not forbidden from doing that. But what you're forbidden is just from having something that is not written as some combination of operators in the subregions. So, what have I gotten? Okay, so what we're saying is that how should we make sense of this? The suggestion is that we should see this situation in terms of this trade-off between the availability of a spatiotemporal description, which sort of trades on the availability of this failure of additivity, and taking into account all the possible causal information encoded in a certain operator algebra, so as some notion of causal completeness, which, as we have seen in some sense, is what additivity ensures. The emergent symmetry, in this sense, is a natural way to keep track of this trade-off, in the sense that as we go towards the semi-classical regime, additivity fails due to the emergence of the new global symmetry, and as a consequence of this failure, and again, thanks to this symmetry, spacetime emerges. So we sort of lose some of the nice causality properties of our quantum field. In exchange, we sort of get gravity out of it. And if we insist on having these nice causality properties, then we lose gravity and spacetime. So sort of let's look a bit at the consequences of this. So what follows from this particular mechanism of space-time emergence? So a first point that emerges from this discussion is that this trade-off between space-time and causality, which is encoded in the failure of additivity. Another way of thinking about this point is that the larger the failure of additivity, in some sense, the more the fundamental description is different from the causal one. If there is just one more operator, we are almost there with the fundamental and the causal one, but if there is a lot of new operators, the failure of additivity is really large, then in some sense we are losing a lot of information. This is especially evident when we think of the evaporating black hole. Late in the evaporation of a black hole, the interior becomes holographically encoded in the Hawking radiation, and this behavior implies a very large failure of additivity, because the union of two radiation subregions has a much larger algebra than the two regions, since it also includes the interior, which leads to a failure of locality. The interior ends up being encoded in the space-like radiation region, while allowing for a geometric description of the interior. So it sort of manifests itself in the loss of some nice causality property, but at the same time it allows us to get a nice geometric description of the interior. And to sort of again keep track of this, you can think of that as soon as you have more than half of the old radiation emitted from a black hole, then you can recover the interior from the radiation. So if I have like two quarter regions of the radiation region, they will not include the interior, but if I sum them up, then I'm going to get the interior. So in this sense, we can see how the more we insist on recovering this semi-classical geometric picture, the less control we have over causal relation. We start to have seemingly non-local effects. We start to sort of have this kind of phantom observables that we cannot measure just from sort of local algebras that we have access to. Conversely, the more we try to insist on having these well-behaved causality properties, the less we have access to a geometric description. For example, if I insist on everything being additive, I will just not have an explicit geometric description of the interior. I will only have the radiation algebra, to which the interior degrees of freedom get mapped, but I will not actually see the geometry of the interior. Indeed, this trade-off is quite interesting because causality and geometry it signals a significant departure from the way that causality and geometry are treated in GR. In GR, for example, we have results like Malamud, where we see that there is a tight connection, almost an equivalence, between geometry and causality. In holography, on the other hand, the two are competing with each other. The more we insist on causality, on causal well-behavedness, the more sort of we lose a geometric intuition for what's going on, and vice versa. And this trade-off I want to suggest leads to two different ontological pictures for quantum gravity. One that is based on this geometric picture, and that basically treats quantum gravity as a quantum field theory of the gravitational field, and one that is based on causality, which gets us back to holography, as I was saying before, since there these failures of additivity are only emergent. We can sort of get an intuition for what's happening here in this way. If we want to privilege the geometric picture, we will demand that the global symmetry leading to failures of additivity is really a fundamental symmetry. Because if it's emergent, then failure of additivity and geometry are also emergent. In particular, it seems reasonable that there should be at least some states which are invariant under all these symmetries. However, as is pointed out here, these states will not obey the Bekenstein-Hawking formula, the Bekenstein-Hawking world entropy formula. The point here is that demanding invariance under all global symmetry gives, for example, if we are in a black hole background, gives time translation invariant backgrounds. And this allows us to do canonical quantization in a black hole background, but, and this was a point that was originally discussed in the 70s by Gibbons and Hawking, won't give you the black hole entropy formula. You can't get the black hole entropy formula if you have this kind of time translation invariant backgrounds. At the same time, since preserving all the symmetries of this background allows us to do canonical quantization, we can sort of think of what we are getting out of this procedure as a somewhat standard quantum field theory of the gravitational field. So in some sense, we are getting an object that is kind of a quantum analog of what we've always been doing when we were doing quantum field theory, just with that gathered into the picture. But we lose these sort of very suggestive and fundamental properties of gravity. Now, on the other hand, if we wish to privilege causality, we will end up thinking of these global symmetries as emergent, and we won't demand that there are any states invariant under them. At least this won't be necessary because they're emergent symmetries, so it might be the case that they're always broken, for all we know. Now, this can be accomplished, as discussed again in this paper by Arlo and Julian, by dropping down the requirements for doing canonical quantization and just quantizing GR using Euclidean path integral techniques. Now, there is a way to sort of think of this still as canonical quantization, but it involves basically assuming holography already. But the point here is that these path integral techniques will lead to a fundamental ontology of quantum gravity, which is going to be additive and holographic. Indeed, the point here is that, as I was telling Nick before, lack of global symmetries is even going to be a theorem of ADS-CFT. And the point basically here is that this Euclidean path integral way of quantizing gravity in ADS will include necessarily some of those symmetry breaking effects that we were talking about before. So it will ensure the Bekenstein-Hawking entropy, and it will ensure that this emergent symmetry is broken in the right way. However, the problem, of course, with this perspective is that it's not really a perspective that allows us to think of the fundamental description as some kind of quantum field theory for gravity, because, again, we are sort of losing these symmetries that we are associating to the existence of a geometric description. And this sort of reflects the preeminence of causality over geometry. Now, finally, I don't know how much time we have. Let me comment on the connection between these two views and these discussions on the causal theory of spacetime. Let me first comment on the connection in spacetime emergence. So under the first geometric view, this emergence of spacetime is understood in rather traditional terms as a kind of effective field theory. And in particular, then we can think of this as a type of emergence that, following the work of people like Butterfield, is going to be compatible with reduction. On the other hand, if we are privileging causality, we obtain an ontology that is significantly more distant from that of gravitational field theory, and so the tools of effective field theory, the standard tools of effective field theory that are associated with this emergence analysis, are going to be much more difficult to apply. In particular, what can be shown is that there won't be any canonical map between this non-additive semi-classical field theory and the additive fundamental description. There is no privileged way to map them. It's always somewhat arbitrary how we decide to do this. In this sense, then, there is going to be no obvious way to have a reduction here of the spacetime picture to the fundamental quantum gravity picture, and so we cannot have a notion of emergence that is going to be compatible with reduction. Here, whatever notion of emergence is appropriate is going to be incompatible with a straightforward notion of reduction. Because the two sides are basically too different to be reduced to each other. Now, this observation ties in interesting with recent discussion on this extending these causal theories of spacetime to quantum gravity in terms of these non-identity causal theories of spacetime. Now, here the main claim of the non-identity theory is that there are some fundamental, possibly quantum gravitational causal relations which ground but are not identical to emergent GR spacetime relations. And this approach has been criticized, among other things, because it is unclear in which sense this non-identity theory is really anything to do with quantum gravity and could not just be formulated as successfully just in terms of GR, which would then make the appeal to quantum gravity unnecessary. Now, while I agree that the examples that Sam Barron and Baptiste consider suffer from this criticism, the specific example that we have here shows a sense in which this non-identity theory does depend, at least sometimes, on purely quantum gravitational considerations and can play an important explanatory role in understanding emergent spacetime. In particular, here again, the trade-off between causation and geometry that we discussed shows a precise sense in which quantum gravity is needed for a causal theory of spacetime. In the causal picture, spacetime emergence is predicated on a failure to properly describe the underlying quantum causal structure. In the geometric one, in order to save geometry, we have to accept a somewhat pathological and possibly non-fundamental causal structure. In either case, what we cannot do is that we cannot rely on GR to construct a causal theory of spacetime, since GR's geometric properties end up being in contrast with having a satisfactory causal structure. at least if by satisfactory causal structure, when we're dealing with the theory of gravity, we mean one that has that is complete and additive. So, conclusions, and I'm done. As we have seen, a crucial role in accounting for the emergence of spacetime is played by the emergence of certain global symmetries in the semi-classical limit. These symmetries, in some sense, quantify the extent to which spacetime and even weakly coupled string theory emerge. Moreover, these symmetries also show that there is an interesting and important trade-off between causality and geometric properties, which has some interesting implication for the ontology of quantum gravity and the SCFT. And that will all. Thank you.
Yeah, thank you very much, Enrico. Very interesting. Maybe you could take a seat over there so I can talk to you. Yeah, this was a very intriguing discussion of gravitational spatial temporal structure on one side and causal structure on the other side. A strong consequence, which I also see in what you built, is that you kind of provide a concrete argument from holography as to condensation maybe insufficient. You often hear that kind of holography makes such a point, but here you kind of see it really spelled out, and I think it's really a merit of his work. And now we'll focus mainly, it's probably expectable, on this non-identity series, so the consequence I find a bit debatable here, but let's discuss, right? Maybe first a bit of a repetition of the physical picture just to make sure I got it correctly. So non-intuitively we have the ADS-CFT correspondence with additivity on the CFT side, and where in a way effectively the CFT side is definitional of the ADS side. And then the perturbative regime, additivity fails, we get some global symmetry, and then also related to that, gravitational and that sense spacetime features rise, for instance, standard entropy formulas like the Cardi entropy formula. Okay, let's skip this question. Let me start with this one. I think it's more instructive. It's not really related maybe to the slides you now use, but to your original slides, and maybe you corrected it. But anyway, I think it might be helpful just for me. So, this original slides, you were using the notion of symmetry breaking.
Yeah, no, I use those here.
Oh, you also use it here?
Yeah.
Okay, I can perfectly better. So I take the setup to be something like this, so that d-dimensional, manifold, spacetime if you want in some sense already, where n dimensions are compactified. So this somehow corresponds, let's say, to the bulk, right? Let's say we are already now in the perturbative regime, and then the idea is you can think of the compactified dimension as somehow cycles, right? And there's an interesting property, depending on whether the cycles are contractible or not. If these cycles are non-contractible, then you can basically characterize them independent of their, or you can characterize the physics related to the cycle independent of the size of the cycle. But if these cycles are contractible, then they do depend on the size of the parameter. Okay, and so what you see is if you have a symmetry, if you have a symmetry, then on a certain amount of cycles, this will establish exactly the fact that this depends on the size. But I'm just wondering, where does the symmetry break come in? I mean, there's this one specific cycle where you might say you don't even have the symmetry. But what's really important is that it's contractible, right? Why does this global symmetry need to be broken? Or where does it get broken? Which regime? Maybe give this as a question first to you, so you can,
So when you have a contractible cycle, that does break the symmetry. It's not going to be translation invariant anymore, for example.
Yeah,
so
but what about specifically the center symmetry? Is also going to be broken then if you have a non-contractible cycle?
No, if the cycle is non-contractible, the symmetry is preserved. If the cycle is contractible, for example, translation and center symmetry in that direction are broken.
Okay, good.
So you can see it easily with translation, right? Because if the cycle contracts, then it's not the same if I translate.
Okay, fair enough. So, but then in a way, it's just a global symmetry which is not fully instantiated from the beginning. It's not like a dynamical symmetry breaking or something like this, right? It's really
no. It's well, that depends. So that was the point about the distinction between geometric and causality. want to take this geometric picture, then you will probably want to say that actually this is a fundamental symmetry, and then there's gonna be at least some state which is invariant under this all the symmetries, not just so where the symmetry is actually instantiated.
Yeah.
And then in that sense, it's when and then you're not gonna have the Bekenstein-Hawking entropy.
But it seems sufficient that you have, let's say, the microscopic level no symmetry, then you get the symmetry, so to speak, partly for everything but this specific cycle, which is supposed to be contractible. But I mean, once the symmetry has emerged, it's just important that it's kind of emerges partly, but there's no no mechanism of breaking anymore.
No, not in the holographic.
Yeah, okay.
If you do holography, indeed, it always needs to be broken in at least one direction.
Okay.
That's the conjecture.
Okay. Yeah, this is helpful. Okay, so maybe this illustrates a bit what's going on in terms of concrete mechanism. Let's move on to the philosophy. There is Baptiste and Thames causal theory. Let's look at the abstract. We developed a new version of the causal theory of spacetime, whereas traditional versions of the theory seek to identify spatial-temporal relations with causal relations. The version we developed takes causal relations to be the grounds for spatial-temporal relations. And then there's also the idea that this answers to certain traditional problems, especially from the causal indolence, its causal indolence problem. And as a matter of fact, they discuss then three types of theories: identity theory, so spatial-temporal relations between events identical to causal relations, and then what they propose themselves, the non-identity causal theory, spatial-temporal relations between events are grounded causal relations, and then a kind of a refined, specific version of it in the context of causal sex theory, right? When we talk of non-identity theory in general, I guess we always, first of all, want to say there's some form of grounding going on between spatial-temporal relations and causal relations. Okay, now a slide from Enrico Cinti here, who tells us that the specific example considered shows us a sense in which non-identity theory is clearly dependent on gravity considerations and can play an important explanatory role in understanding spatial emergence. So my first question would simply be, sorry, it might sound a bit provocative, it's just me to explain for you, what deeper explanatory role is played by the non-identity theory in your case? In general, does it do more than summarize and illustrate the physics here? At what level do you take the explanation to take place? What kind is it?
I think it gives you an ontology that underpins the sense in which there is a trade-off. That's the point. So if you think that space-time is grounded in the existence of these causal relations, then in some sense, what you end up saying here that explains, in some sense, the emergence is that the emergence of space-time is connected to the fact that you basically start ignoring a bunch of these fundamental causal relations. That allows you to define a global symmetry, and that global symmetry corresponds to the appearance of space-time with the symmetry breaking caveat that we talked about before. So that would be the idea, in which it can still play some kind of explanatory role. It gives you some type of metaphysical picture that underlines this type of trade-off that otherwise you might have a different one. But that was just one sense in which I thought this non-identity theory might actually be interesting here.
Yeah, is explanation in the right word, or maybe explanation in the sense of kind of you subsume it into a general picture like this, or you?
I guess you could also use the word interpretation. I suppose
okay.
some kind of interpretation, interpretative role that is played by this.
Yes, sorry for me. I just kind of.
No.
So I just need to. Okay, then it's even more petty. So, question 4: how can one show the proposal for a non-identity theory needed for probability consideration? What would you needed to show that? Or is the question really, the point really that your kind of probability consideration they render non-identity theory more necessary, in particular, as opposed to mere identity theory? That's kind of what you mean by it. But if that's the case, then I have some follow-up question. I mean, first of all, to what extent is this non-identity theory really well motivated in the case considered? I mean, you talk a lot about this trade-off. I mean, and it's very interesting indeed. But to what extent does the case considered really establish that one layer is just spatial-temporal and the other one is just causal? I mean, for instance, I could equally talk here about a trade-off between causal structure and causal structure.
Yeah.
I mean, CFT on the CFT side and the GR side. If we drop into this kind of algebraic QFT language you introduced, we can also talk easily about a trade-off between space-time and space-time structure. I mean, you don't have to equate space-time to gravitational space-time. Conformal space, conformal fields you find on a more symmetric space-time. Yes, no sense of scaling and so on, but in a way, still space-time. And kind of from a different angle, to what extent is the 990 theory here really so interesting? I mean, why do you morph this horizontal question of, I mean, it's also Baptiste, I'm sorry, this is not meant as the tag, it's just a general question here. Why morph the horizontal question of causal reformability of the theory into a vertical one of grounding here? I mean, just take this following example. Can Newtonian gravity be given a geometric formulation? You can compare this question to the question, can force relations etc. be grounded in geometry? And well, the questions are very different and of very different interest. For instance, we have learned at some point that there's a geometric formulation of Newtonian gravity, Newtonian Catard theory, and it's very different from the lesson that we could always reproduce Newtonian gravity in the limit of GR. I mean, okay, maybe you have a very specific view on how the limit works. So I mentioned the Ehlers frame too, but yeah, first of all, there seems to be very different ways of thinking, and so maybe also as a kind of quick general criticism of this program of non-identity theory, I mean, how much is really in the tradition, in what sense do you really rescue, so to speak, the causal story about GR, which after all, as you mentioned yourself, is kind of vector field theory, which lives in its own domain, and so on. Yeah.
Can you go back to Q4?
Q4 is here, exactly,
Yeah, so here the sense in which I was saying that it needs quantum gravity considerations is that at least in the proposed example, you cannot really use, if you use this notion of completeness, of sort of causal niceness that I'm using here, you cannot really construct a causally nice net of operator algebras, for example, for GR. So in GR you cannot. So in that sense, so there is a background sort of assumption that when you say you want a causal theory, what you mean is that you want a causally well-behaved theory in that sense.
Right.
If you're fine with having a causally well-behaved theory simply in the sense of like Malamud's theorem, where he just tells you something like, well, just causal connectibility is enough, then of course you can always do that in GR because you have a theorem that tells you that in GR you can do it. But the point here is that you cannot have the specific type of causally nice theory that I've been discussing. So in that sense, you need quantum gravity to have the causal thing that then grounds the spatio-temporal relations. So that was the idea as to why you need this quantum gravity consideration.
Yeah, I mean, just a quick reply, I would just say even GR can be set up in such a way that you're saying you can talk about a non-entity theory of space-time grounded in causal structure. So I would probably contest this a bit, but...
So in the background here there is a notion that when one says, like, at least for me the point here was that when we talk about causal relations, we mean causal relations that satisfy some of these axioms. If they can be just, if you just count as causal relation, basically just causal connectibility, then of course you can do what you described just now. But the point is that you want these causal relations, at least here, and that sort of goes back to what I was saying before. You have some decent reason to think that you want your theory to have. You want whatever theory you use to explain space-time to have those nice causality properties. So you might want to think that those are, at least for a gravitational theory, those are actually properties of what it means to be causal. Because at the end of the day, you're going to need them. And that forces you to have a theory that you cannot formulate just using GR. If you're happy with just dropping additivity, then you're going to be able to do this in the context of GR, but then there is going to be a sense in which whatever you end up doing in quantum gravity is going to be strange. There's going to be these strange situations where you have operators associated to like large regions that are completely inaccessible to you. And there is no way for you to, like there is a charge that you have no idea what it is, where it comes from, what it does. It's just completely screened off from you.
Sounds a bit to me though as if to have a non-identity theory non-identity theory of GR, you want to look at it necessarily kind of a non-identity theory of your case, which of course it involves, so to speak, by setups, this QG considerations, but okay, I see. Okay.
No, so the idea was that for this type of example at least, there is no obvious sense in which, so at least you have one example where you actually seem to need these quantum gravity considerations. In complete generality, of course, I agree that you can, because to some extent you do have constructions in GR where you can do that.
Yeah, I think in your example you need it because it involves QG considerations. Right?
Yeah. In this example you need, like the non-identity theory involves quantum gravity consideration.
Yeah.
You cannot do the non-identity theory here, considering sort of this completeness of algebras without, you cannot do it in GR, basically. Now, can you go to Q5?
Yes.
Thank you. So to what extent does it... Yes, so okay, so this goes back to sort of to something I was saying at the start as a bit of setup. So let me tackle the second question rather than the first one first. So here the idea is that I talk for, again, simplicity of CFT most of the time, but really that is supposed to be whatever microscopic description one has. That microscopic description in general is not going to actually involve the Minkowski background in which a CFT is defined. So a CFT as a quantum field theory is usually defined in an equivalence class of metrics under conformal transformations, which includes the Minkowski background. So you can always write it as a theory in Minkowski. The problem with this is that that's true for the CFT, it's presumably not going to be true for whatever the actual microscopic theory here. So if you write down something like a common core theory, for example, that is most likely not going to involve any recognizable notion of space-time at the fundamental level, because exactly that type of Minkowski background is the type of thing that won't be defined. It's going to be part of whatever the specific structure is going to be.
Right. In a way it's true, and of course then you're really interested in the common core lesson, right? I mean, as opposed to that you're afterward at the moment at least just using a CFT at the bottom, right?
Yes, I am assuming that, what I am assuming is that, at least for the purposes of this discussion, what we don't want to do is that we don't want to assume a very specific view on the correct interpretation of dualities.
Yeah.
So we want at least to tell a story, until we know sort of what the common core theory looks like for the microscopics. At least I would like to tell a story that is independent of what we choose. And this specific story, where we talk about a trade-off between space-time and space-time, is going to be actually quite dependent on basically taking an approach where the fundamental theory is the actual CFT. It's not like some common core theory or anything else. Like it needs to be the CFT.
Yeah.
Because the structure is really going to be only there.
Even with your story, right? Because it also really stresses
we're taking a bit long, I'm sorry. Because I was answering the question of the comment, but we are taking a bit long, you're right.
Sorry, I've been sharing that.
No, I'm sorry.
I'm really enjoying the discussion. So
You should join the discussion. It's my fault. I'm just taking too long to reply.
Alisa, please go ahead.
No. Sorry.
I just wanted them to stop, actually.
Okay, we didn't get to the last one is a question to you, I guess. So you can answer better. Please.
Oh, well, maybe I was just in that was one of the questions I was kind of confused because in the beginning when you were talking about ADS CFT, you were like, but of course most people think that the CFT is not the fundamental theory. And I mean, sorry, that the claim of So I know, like philosophers, a lot of the philosophers, we've argued that you don't get, from the duality, you don't get a claim that one of the theories is more fundamental, but I thought in the physics community, the people that are working on bulk reconstruction and that are advocating for this as a non-perturbative theory of quantum gravity are thinking that the quantum field theory is fundamental, and it seemed like your whole talk was premised on that. And you're still talking that way. So I don't know, what was the little aside about?
So,
why did you get that little aside? What was,
So it's true. That is actually very interesting. So it is true that the average paper that uses stuff like bulk reconstruction usually they basically talk as if you are reconstructing stuff from the CFT in the bulk spacetime. They are shown that what is unclear is always how much of this is language and just the fact that one sort of speaks that way because it's convenient, and to what extent it's supposed to be some substantive assumption about how to make sense of the physics. When they are somewhat more careful, they do actually spell it out in a way that is closer to what I'm saying here. So they do say there is this paper on non-isometric quantum error correction in holography by the whole Bengelart, Arlo, Pennington collective, where they do actually spell it out more or less they spell it out in very similar ways. So they tell you, well, really there is this fundamental description which we use the CFT to define, and which just describes the microscopic theory underlying the semi-classical spacetime, and then we have some semi-classical description, which is just the bulk semi-classical gravity Hilbert space in that case, because I'm working with Hilbert spaces. So in that sense, I am not completely sure that physicists speak as if the microscopic theory is the CFT. When pushed, I'm not entirely sure that they would actually agree that it's just really a literal CFT in the sense, in the strong sense that I think Niels had in mind in that question. So yes, there is let's say we're doing ADS5, CFT4, there is a 4-dimensional Minkowski background with some conformal fields on top of it, and something along those lines, because one presumably also then would want to have string theoretic considerations behind that, and the whole story would become more complicated. So the aside in that sense was basically this, that I do take a lot of the physics literature when they speak about the CFT as fundamental to be mostly referring to the CFT as fundamental as just the claim that the CFT is fundamental to be mostly a linguistic claim of just ease of exposition to a large extent, and whatever the precise story about the ontology needs to be worked out in a bit more detail. Because I do take a lot of I personally do find the arguments by philosophers on this quite convincing. So I do think that the claim that there cannot be emergence sort of across the duality to be reasonably convincing. Because basically the duality is a symmetric relation and emergence is not. So one cannot combine the two in that way. So I do take the physics papers in this sense to be somewhat imprecise in a way that makes a lot of sense to me. Exactly, because it seems that sort of when they try to be a bit more precise, what they really are speaking is something like the microscopic Hilbert space defined using the CFT, or the semi-classical bulk Hilbert space defined using something like semi-classical gravity. And that's also why I was basically saying that then I don't want to take the boundary CFT as sort of whatever the fundamental object, the fundamental ontology of this theory is given by, in the sense that Niels had in mind. So where we literally say that there is some CFT spacetime, some conformal spacetime with some fields on top of it.
So I'm going to just, I'm going to speak first, sorry, it's a bit rude, but I will just do it once on the chat. I think you said you didn't want to commit yourself to the, so far that's great, I love it, thanks a lot for that. You don't want to to commit yourself to the existence of relational relative fundamentality between you have one side of the dual iteration, the ADS CFT. But in fact, from what you just said now, it seems like you are quite driven by a common core approach, something like that.
I have some sympathy for that.
Yeah, you have sympathy for that, but I was thinking just in terms of articulating things, instead of saying I'm not going to commit myself, you could say, well, what I'm doing is consistent with two different scenarios.
Yeah.
Scenario one, the causal structure is located in the common core.
Yeah.
And space-time is grounded in this common core. Option two, you break the symmetry of the duality and say one side you have a discriminatory approach, say one side of the duality is more fundamental than the other, and then you locate the causal network on one side, right?
Yeah.
And you might say, well, I have my preference, but I don't want to commit myself. Because I think some of the discussion was going from one to
So let me maybe try to explain what I have in mind here. So
I think I understand what you have in mind was more like...
No, that makes a lot of sense. Well, it's just that I'm somewhat worried that if one goes down the route where one just takes completely seriously this discriminatory approach, where just the CFT is whatever is fundamental, then yes, I mean, what Niels says makes a lot of sense, because at that point one just says you're moving from one space-time to a different one.
But I mean, here is the point, you don't want to say it's absolutely fundamental, right? We could have the duality, even if the CFT side is not absolutely fundamental. You could have an equal fundamentality, and that would still be compatible with the claim you made that the CFT side should not be taken too literally, because we expect that there is an even more fundamental description on this side. So I think that would be
okay. Yes, but yeah, no, okay, that's fair. That's fine.
But I mean, that's just a small.
Yeah, that makes sense.
But anyway, I'm going to have many things on Instagram. I'm going to.
Yeah.
I mean, so this was again on the same on replying to what you adding to what you said to Alyssa. In the Beyond Spacetime collection, there's a nice paper there by Harlow that talks about exactly this issue in a non-sort of text. Okay. And it is pretty much what you say. He kind of buys the philosophical arguments. I think that duality would be a sort of symmetric relation with respect to the fundamentality, but he makes the point the actual CFT is a more, the formulation you have on the boundary is a more fundamental than the semi-classical.
Like if one...
Isn't that right? I think he kind of endorses that sort of picture.
Yeah, but part of what he was doing there was to say, like, well, this is still like a classical space-time, and there's like, so what we're doing is we're relating some kind of quantum theory to this classical space-time, but then there's still going to be some more fundamental, like more fully quantum picture underneath, and then, so it's not like the thing that gets related by the dualities is like at all the fundamental story, right? Isn't that kind of what he was doing?
Yeah, that's right. And I think that's what you were saying.
Yeah, that's exactly what I have in mind. So like that's like you can basically write down like a diagram that kind of looks like this. So like you're gonna have like GR, and GR is gonna be in some sense dual to something that is like a CFT for like n going to infinity. Okay. And then the CFT, of course, you can define it at finite n. So for n, something. And there is also going to be some Cauchy gravity that we don't really know, and there is also going to be some map here. And then oftentimes, what entanglement wedge reconstruction is basically in the business of doing is really just relating this object, so a finite n CFT, to this object here. So that's, and that's the sense in which I was talking about this as the fundamental description and this as the semi-classical description. You can also just work with the n to infinity CFT. N to infinity is just the same as taking G Newton to 0. The reason why you don't do it is basically because you don't really get entanglement wedge reconstruction here, you just get causal wedge reconstruction. And it follows in the algebraic language from something that's called like the time-like tube theorem. So basically, if you think of like, if you think of an ADS space-time of some kind, like let's take an ADS black hole, then the thing that if you work with this theory, which is exactly dual in this sense to a GR theory, then at most you will will be able to reconstruct whatever is causally accessible from the boundary. So this region here, the exterior. While entanglement wedge reconstruction, as we've kind of seen, if you have enough information, you're going to be able to access also the interior at some point. That's it. So, but you need this finite n contribution. Otherwise, you only have causal wedge reconstruction. So, if you want, there is a sense in which this has EWR, and this only has CWR. And what we want is entanglement wedge reconstruction, really, to say all of these things. So otherwise, well, causal wedge reconstruction doesn't really allow us to say much. Does it make sense? Maybe the aside about entanglement wedge reconstruction was not really helpful. But this is the diagram.
Can we have any more question, or we let Niels continue? No, I mean, it's a great discussion. I just want to think everybody has the occasion.
Everyone else is happy to say that one.
Yeah, go ahead.
Thanks. So it was very interesting. I just have several questions. I guess we'll have time afterwards. I just wanted to know a bit more about. First one is more clarificatory, and at a certain point you mentioned the fact that the larger the failure of additivity, the more difference you will expect between fundamental and the emergent, you call it this way. And how do you track that? Is it in terms of like the volume and the bark?
No. So in the field theory, unfortunately, so that's a bit annoying to track. So in the field theory, what you would like to have is some type of index that measures this. Now, for failures of additivity, I don't know if someone has actually constructed, if you want to do it precisely, I don't know of an index that has been constructed. There is a basically completely analogous discussion to this, but for a different property, which is called hard duality, which is basically it's another property. There you can define an index. It's the same thing. You see that global symmetries lead to violations of this hard duality property, and you can measure how much hard duality is violated, so how distant you are from a theory that satisfies this property with an index. And the larger the number is, the more it's violated. The reason why you don't use hard duality is because it's quite unclear how to make sense of it holographically. So holographically, hard duality seems to be actually a property that you have all the time. So it's somewhat unclear, it's difficult to make sense of it in this quite nice sense in which additivity is. So there is an intuitive sense, and there is a sense in which, because there is a construction really in the vicinity of this, that basically, where you have an actually precise index. I don't know that there is an index in the context of additivity that you can use.
Okay, good. And the other thing is like broader, namely, because I find very interesting this way of framing the issue of like having these two different ontological commitments. It's just that I haven't quite got a chance to really understand, maybe I wasn't following enough the discussion on what motivation we have to favor a certain representation, and so how do you actually establish the proper trade-off between these two ways of
I think it's just it's a theory building problem. So it depends exactly, like if you want, for example, the Bekenstein-Hawking entropy to hold, you're going to treat all these global symmetries as completely emergent. You're not going to have them at the fundamental level, really. So that's what happens in holography. But if you, for example, do not want the Bekenstein-Hawking entropy to be an actual bound on your count of degrees of freedom, for example, so if you're happy with having states that do not obey the Bekenstein-Hawking entropy formula, then you might treat it as a fundamental description. And that might give you, this geometric description might treat it as fundamental, and that might give you all kinds of advantages. It's not really, what's called here a geometric description is not really something that has been explored too much, because it's usually, I have some sympathy for that, considered as a bit pathological, exactly because it doesn't satisfy it doesn't get you the right entropy formulas. But if you're happy with that, you can. It's what you get, like if you take, to some extent, it's what you get if you just do sort of the most straightforward application that you can think of canonical quantization to something like a black hole spacetime. Because if you think of the black hole spacetime in like Lorentzian signature, then when you do canonical quantization, you're going to have something like a boundary times a Cauchy slice. That Cauchy slice is going to involve an uncontractible circle in the bulk, which is what Niels was pointing out before. So in that sense, you're gonna have a symmetry invariant state there. In that sense, it's connected to canonical quantization. The problem is that if you do that, you're not gonna get the Bekenstein-Hawking entropy. So that was like one of the starting points for that paper in the 70s by Gibbons and Hawking for why they end up looking at Euclidean path integrals. Because if you look at Euclidean path integrals, you get basically, so the Lorentzian configuration gets you 0, and then you get one where the thermal circle contracts, and when the thermal circle contracts, you get the Hawking term for the entropy, and that gets you the right calculation, basically. So it's going to be a matter of trade-offs, basically. Like if you really care about this very sort of straightforward way of thinking about quantum field theories, where you just do some canonical quantization and you're done, and you want to apply it somewhat straightforwardly to gravity, then you're going to do that. But then you're going to lose all these seemingly very suggestive properties. If you're fine with like leaving that aside and looking at things like Euclidean path integrals, then you're going to be fine. You're going to get the Bekenstein-Hawking entropy, but then you're going to get a theory that is going to be some type of holographic theory, really. Because even formally, the way that the Euclidean path integral solves this issue in some sense is that instead of looking at the boundary times a Cauchy slice, you really just look at the boundary times the boundary of a Cauchy slice. So you just really look at the Cauchy slice, at the boundary of your spacetime. That is in some sense what's happening. That's why you're allowed to include a contracting circle in your saddle point approximation. Does that make sense?
Okay, last part was a bit obscure to me.
Okay.
But
we can write it down.
yeah.
Like it's
yeah.
right. Like if like the point is that you want to include saddles of this form, right?
Mm-hmm.
This is in Euclidean signature. Now the point is that you can only have if you're doing something like canonical quantization, what you're going to get is that you're only going to get saddles of this form. Something like this. You won't get something like this. And this one you can really get only if you basically don't worry too much about doing like at least a very straightforward form of canonical quantization, and you decide that you're happy with doing something like a Euclidean path integral. But this you can sort of see immediately how it leads you to holography. Because really at the end of the day, the only data that you input into the path integral is this boundary data here. So it's like so it's going to depend on something like the size of the thermal circle here, so like this data here. It's not going to depend on like the interior properties of the geometry. So that's the idea. This gets you the wrong entropy count. This gets you the right entropy count.
Do you want me? I feel like Niels should try to say something on this slide. Do you want me to finish by saying something?
Please, yeah.
Because I mean, Niels wrote this paper with Rasmus, and we never replied. But it's because we plan to roll this in the book with Sam. So we're going to use the paper and reply to the paper. But so why not horizontal equation of causal with modality and purity of vertical one of grounding? So it's not morphing, right? In this view, you have horizontal causal relations. But the reason it's more like why would you take from the extent of this horizontal network of causal relations? Why would you take this to be suggestive of a vertical grounding relation? I think so if you have more structure, you know what, somebody suggested it's more fundamental, right? So it gives you an idea that one side is more fundamental, and this more fundamental bit is latching onto the grounding idea. For those two questions, yes, they're very different, sure. Very different interests. Yes, maybe, it depends on the context. So I agree with you that in the paper we're kind of conflating a bit questions about motivations from GL causal theories of spacetime and motivations in general from outside of GL spacetime, but from quantum gravity. We're going to disambiguate two things, but the idea there was not to show that there was a right theory of the world, but not to find an interpretative scheme to make sense of the emergence of spacetime. That was one of the motivations for reviving causal theory of spacetime, but to show that it was potentially helping us to make sense of spacetime emergence, and we were talking about causal set theory. And I think Enrico has been showing that there is one possible interpretation of what's happening with holography, the idea CFT duality, which would be nicely suggesting a non-identity causal theory of spacetime. Perhaps not in a. Anyway, I don't want to speak too much, but just to give you a bit of my reaction to that.
I save it for.
I give you the final word, perhaps, or maybe from Enrico. I'm not sure.
Enrico, please.
No, yeah, that's more or less similar to the way that I was thinking about it. So the point is just there is some natural way of making sense of this scenario, which is using this non-identity causal theory. If you're willing to swallow enough annoying interpretational options, you can get something else. But this is this at least to my mind is a decently nice way to fit it with what seems to me the most natural way to think about the physics, which is why I liked it here.
Yeah, I just don't see the continuity anymore to the original causal theory.
Fair enough.
And then it's really just saying, oh, some kind of X can emerge from some kind of Y, and one option is that this Y is causal theory. And that's what I would reply here, but yeah, we can discuss.
Yeah. All right. Thanks again to Enrico.